Right now, light from distant stars is racing toward Earth, carrying secrets from across the cosmos. But here's what will shatter your understanding of reality. Some of that light began its journey before our planet even existed, traveling through distances so vast that they break human comprehension. Tonight, we're uncovering the cosmic measurement that reveals just how impossibly small we are in the universe, the light year, and discovering why these distances hide mysteries that challenge everything we think we know about space, time, and the very nature of existence itself. Now let's begin. A light year isn't a measurement of time. It's a measurement of distance so enormous that our brains simply weren't evolved to comprehend it. 1 light year equals the distance that light travels in a vacuum over the course of 1 year. Since light moves at roughly 300,000 kilometers per second, a single light year spans approximately 9.5 trillion kilometers. To put that in perspective, if Earth were the size of a marble, a light year would stretch from New York to Los Angeles and back again over 2 million times. The concept of the light year was born from necessity. When astronomers in the 17th and 18th centuries began measuring distances to stars, they quickly realized that traditional units like kilometers or miles became meaninglessly large. Friedrich Bessel made the first successful measurement of stellar distance in 1838 when he calculated that the star 61 Cygni was about 11 light-years away. This breakthrough opened our eyes to the true scale of the cosmos for the first time. But even understanding what a light year represents doesn't prepare us for the staggering distances involved in cosmic measurements. Our nearest stellar neighbor, Proxima Centauri, sits 4.2 light-years away. This means the light you see from that star tonight actually left its surface over 4 years ago when the world was dealing with a global pandemic, and many of us were just beginning to understand how interconnected our planet really is. The Andromeda galaxy, our nearest major galactic neighbor, lies 2.5 million light-years from Earth. The light reaching your eyes from Andromeda began its journey when our earliest human ancestors were just learning to use stone tools. That photon has been traveling through the cosmic void longer than our species has existed, carrying with it information about a galaxy that may have changed dramatically since that light began its epic journey toward us. When we look deeper into space with powerful telescopes like the James Webb Space Telescope, we're literally looking back in time. The most distant galaxies we can observe appear as they were over 13 billion years ago when the universe was just a cosmic infant. These ancient galaxies show us what the cosmos looked like when the first stars were forming, when heavy elements were being forged for the first time, and when the large-scale structure of the universe was just beginning to take shape. The Hubble Space Telescope has revealed galaxies so distant that their light has been traveling toward us for most of the universe's history. The Hubble Ultra Deep Field, a photograph of what appears to be empty space, actually contains over 10,000 galaxies, each one a collection of hundreds of billions of stars. Some of these galaxies are so far away that we're seeing them as they appeared when the universe was less than 1 billion years old. This time travel aspect of astronomy means that every observation is also an archaeological expedition into cosmic history. When we study a star that's 1,000 light-years away, we're seeing it as it was during the time of the Byzantine Empire on Earth. When we observe the center of our own galaxy, 26,000 light-years distant, we're viewing events that occurred when our ancestors were painting caves and developing the first agricultural societies. The scale becomes even more mind-boggling when we consider the observable universe itself. The most distant objects we can detect are roughly 46 billion light-years away, not 13.8 billion, as you might expect from the universe's age. This discrepancy exists because space itself has been expanding during the time that light has been traveling toward us, stretching the distance between us and those ancient sources of light. Our own Milky Way galaxy spans approximately 100,000 light-years from edge to edge. If you could somehow travel at light speed, it would take you 100,000 years just to cross our galactic home. The supermassive black hole at our galaxy's center, Sagittarius A star, sits 26,000 light-years away from us. The Event Horizon Telescope's historic image of this black hole shows us how it appeared 26,000 years ago during the last ice age on Earth. If you're finding these cosmic scales as mind-bending as I am, I'd really appreciate it if you could hit that subscribe button and give this video a thumbs up. We're just getting started on this journey through the universe's most incredible distances, and your support helps me continue exploring these amazing frontiers of science. The local group, our galactic neighborhood containing the Milky Way, Andromeda, and dozens of smaller galaxies, spans roughly 10 million light-years. Beyond that lies the Virgo Supercluster, a massive collection of galaxy groups stretching over 100 million light-years. And beyond that, the cosmic web continues, with superclusters separated by vast voids that can span hundreds of millions of light-years of nearly empty space. These distances become so large that they start to lose meaning in human terms. When astronomers discovered the most distant galaxy ever observed, GNZ11, they found an object whose light has been traveling for over 13 billion years. This galaxy appears as it was when the universe was just 400 million years old, a cosmic baby compared to today's 13.8 billion-year-old universe. The cosmic microwave background radiation, the afterglow of the Big Bang itself, comes to us from a distance of about 46 billion light-years. This radiation has been traveling since the universe became transparent to light, roughly 380,000 years after the Big Bang. Every square centimeter of the sky glows with this ancient light, carrying information about the universe's infancy. But here's where the story becomes even more extraordinary. We're not just passive observers of these cosmic distances, we're active participants in the universe's ongoing story. The calcium in our bones was forged in the nuclear furnaces of massive stars that exploded billions of years ago, scattering their enriched material across light years of space. The iron in our blood was created in supernova explosions that occurred when the universe was much younger, and that material traveled vast distances before eventually becoming part of the solar system that gave birth to Earth and, ultimately, to us. The oxygen we breathe was created in stars that lived and died across the galaxy, their stellar winds and explosive deaths distributing this life-giving element across thousands of light-years. We are literally made of stardust that has journeyed across the cosmos for billions of years, connecting us intimately to the vast scales we're exploring tonight. This cosmic connection becomes even more profound when we realize that the elements in our bodies have traveled unimaginable distances to reach us. The carbon that forms the backbone of every organic molecule in your body was forged in the cores of ancient stars, then expelled into space when those stars reached the end of their lives. That carbon may have drifted through interstellar space for millions of years, covering hundreds or thousands of light-years before eventually becoming part of the molecular cloud that collapsed to form our solar system 4.6 billion years ago. The gold in any jewelry you might be wearing has an even more exotic origin story. Gold can only be created in the most violent events in the universe, neutron-star collisions and certain types of supernova explosions. The gold atoms in a simple wedding ring may have been forged in a cosmic catastrophe that occurred billions of light-years away, then traveled across vast stretches of space and time before eventually becoming part of Earth's crust. When we contemplate these distances, we begin to understand why faster-than-light travel captures our imagination so powerfully. The nearest potentially habitable exoplanet, Proxima Centauri b, orbits our closest stellar neighbor at a distance of 4.2 light-years. With our current technology, a journey to this world would take tens of thousands of years. Even our fastest spacecraft, the Parker Solar Probe, would need over 6,000 years to reach Proxima Centauri if it were aimed in that direction. Speaking of the challenges and possibilities of cosmic travel, if you're curious about what might happen if we could somehow break the ultimate speed barrier, you should check out my video, What If We Could Travel Faster Than Light Speed? It explores the mind-bending physics and incredible implications of superluminal travel, from time paradoxes to the transformation of human civilization. The theoretical possibilities are as fascinating as they are impossible with our current understanding of physics. The link is on the card above and pinned on the comments. The scale of light years helps us understand why the search for extraterrestrial intelligence faces such enormous challenges. Even if advanced civilizations exist around nearby stars, communication would be incredibly slow. A radio message sent to Proxima Centauri would take 4.2 years to arrive, and any response would take another 4.2 years to reach us. A simple conversation would span nearly a decade, making real-time communication impossible across even the shortest interstellar distances. The Kepler Space Telescope, during its 9-year mission, discovered thousands of exoplanets orbiting stars hundreds and thousands of light-years away. Each of these worlds represents a story that began long before humans existed on Earth. The light we see from these distant planetary systems carries information about events that occurred when dinosaurs roamed our planet, or when the first multicellular life was evolving in Earth's ancient oceans. TRAPPIST-1, a fascinating planetary system containing 7 Earth-sized worlds, lies 39 light-years from our solar system. The light we observe from this system today actually left those planets in 1984, when personal computers were just becoming common and the internet was still a decade away from widespread use. If there's life on any of those worlds, we're seeing it as it existed during the Reagan administration. The James Webb Space Telescope has revolutionized our ability to peer across these vast distances, revealing galaxies that formed when the universe was less than 5% of its current age. These ancient galaxies appear surprisingly massive and mature for their cosmic youth, challenging our understanding of how quickly large structures could form in the early universe. The light from these galaxies has been traveling toward us for over 13 billion years, crossing distances so vast that they dwarf our local galactic neighborhood. When we observe the cosmic microwave background with instruments like the Planck satellite, we're detecting radiation that has been traveling for 13.8 billion years. This ancient light has crossed the entire observable universe, carrying with it the imprint of tiny fluctuations that would eventually grow into the galaxies, stars, and planets we see today. The patterns in this radiation tell us about the universe when it was just 380,000 years old and had a temperature of about 3,000 Kelvin. The concept of look-back time becomes crucial for understanding cosmic evolution. When astronomers study galaxies at different distances, they're essentially conducting an archaeological survey of cosmic history. Nearby galaxies show us what mature galactic systems look like after billions of years of evolution. Galaxies at intermediate distances reveal how galactic structure and star formation have changed over cosmic time. The most distant galaxies provide snapshots of the universe's youth, when the first generation of stars was just beginning to illuminate the cosmic dark ages. The Sloan Digital Sky Survey has mapped over 3 million galaxies across billions of light-years, creating a 3-dimensional map of cosmic structure that reveals how matter is distributed throughout the universe. This survey shows that galaxies aren't randomly scattered through space, but instead follow a cosmic web of filaments and voids with dense clusters connected by tendrils of dark matter, spanning hundreds of millions of light-years. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, stretches over 10 billion light-years across. This massive collection of galaxy clusters is so large that light takes over 10 billion years to travel from one end to the other. The existence of such enormous structures challenges our understanding of how the universe evolved and raises questions about the fundamental nature of cosmic evolution. When we consider the speed of light as the ultimate cosmic speed limit, these distances become even more staggering. Information cannot travel faster than light, which means that events happening right now in distant galaxies won't be visible to us for millions, billions, or even tens of billions of years. We're forever isolated from the present moment in distant parts of the universe, able to see only their ancient past. This isolation has profound implications for our understanding of cosmic evolution. The universe we observe is a patchwork of different epochs, with nearby objects showing us the recent past and distant objects revealing the ancient past. We can never see the universe as it exists right now in its entirety. We can only piece together its history from the light that has had time to reach us. The expansion of space itself adds another layer of complexity to these distances. The universe has been expanding since the Big Bang, which means that galaxies we observe at great distances are actually much farther away now than they were when their light began its journey toward us. A galaxy whose light has been traveling for 10 billion years might now be 15 billion light-years away due to cosmic expansion. Dark energy, the mysterious force driving the acceleration of cosmic expansion, ensures that this stretching of space will continue indefinitely. Galaxies beyond our local group are receding from us at ever-increasing speeds, and eventually they will cross the cosmic event horizon and disappear from our observable universe forever. Future astronomers, billions of years from now, will see a much emptier cosmos than we do today. The cosmic microwave background represents the most distant light we can ever hope to observe. Before the universe became transparent to light, roughly 380,000 years after the Big Bang, photons were constantly scattered by free electrons and protons. This cosmic fog prevented light from traveling freely through space. The cosmic microwave background marks the moment when the universe cooled enough for atoms to form, allowing light to stream freely across cosmic distances for the first time. The cosmic microwave background represents the ultimate horizon of our observable universe, but it also reveals something profound about the nature of space and time. This ancient radiation shows us that the universe was once much smaller, hotter, and denser than it is today. The tiny temperature fluctuations in this background radiation, detected by satellites like WMAP and Planck, represent the seeds from which all cosmic structure would eventually grow. These primordial fluctuations were stretched across the cosmos by cosmic inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During inflation, regions of space that were initially smaller than a proton were stretched to sizes larger than basketballs in an incredibly brief moment. This process took quantum fluctuations and amplified them to cosmic scales, creating the foundation for everything we see in the universe today. The Atacama Large Millimeter Array, or ALMA, has allowed us to peer through cosmic dust and observe star formation in galaxies billions of light-years away. These observations reveal that the peak of star formation in the universe occurred when the cosmos was only 2 to 3 billion years old. We're seeing these ancient stellar nurseries as they appeared when the universe was just beginning to hit its stride in terms of creating the heavy elements necessary for planets and life. The light from these distant star-forming regions has been traveling toward us for over 10 billion years, crossing vast stretches of space that contain dark matter, dark energy, and ordinary matter in proportions that we're still trying to understand. Along the way, this light has been stretched by the expansion of space, shifting it from visible wavelengths to infrared and radio wavelengths that require specialized telescopes to detect. When we observe supernovae in distant galaxies, we're witnessing stellar explosions that occurred billions of years ago. Type Ia supernovae, which serve as standard candles for measuring cosmic distances, have revealed that the expansion of the universe is accelerating. This discovery, made by studying supernovae at distances of billions of light years, led to the realization that dark energy dominates the universe's energy budget. The Hubble Space Telescope's observations of Cepheid variable stars in nearby galaxies have allowed astronomers to calibrate the cosmic distance ladder with unprecedented precision. These pulsating stars, whose brightness varies in a predictable pattern related to their intrinsic luminosity, serve as cosmic lighthouses that help us measure distances across millions of light years with remarkable accuracy. But even our most precise distance measurements reveal puzzling discrepancies. The Hubble constant, which describes how fast the universe is expanding, gives different values depending on whether we measure it using nearby objects or the cosmic microwave background. This Hubble tension suggests that our understanding of cosmic distances and expansion might be incomplete, pointing toward new physics that we haven't yet discovered. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey hundreds of millions of galaxies across billions of light years, creating the most comprehensive map of cosmic structure ever assembled. This survey will help resolve the Hubble tension and provide new insights into the nature of dark energy and the evolution of cosmic structure over vast distances and timescales. Gravitational lensing provides another tool for probing cosmic distances and the distribution of matter throughout the universe. When light from distant galaxies passes near massive objects like galaxy clusters, the gravitational field bends the light's path, creating distorted or multiple images of the background galaxies. These gravitational lenses can magnify distant objects, allowing us to see galaxies that would otherwise be too faint to detect. The most extreme gravitational lenses can magnify background galaxies by factors of 10 or even 100, effectively turning massive galaxy clusters into natural telescopes. Through this cosmic magnification, we can study galaxies that are so distant their light has been traveling for over 13 billion years, revealing details about star formation and galaxy evolution in the very early universe. Fast radio bursts, mysterious signals that last just milliseconds but release enormous amounts of energy, have been detected from distances of billions of light years. These enigmatic events, first discovered in 2007, provide new tools for studying the intergalactic medium and measuring cosmic distances. The dispersion of radio waves as they travel through ionized gas between galaxies can reveal information about the distribution of matter across cosmic scales. The Event Horizon. Telescopes' groundbreaking images of supermassive black holes in M87 and our own galaxy represent observations across vastly different distance scales. M87's black hole lies 55 million light-years away, while Sagittarius A star sits 26,000 light-years from Earth. Both images required coordinating telescopes around the world to achieve the resolution necessary to see these cosmic monsters directly. When we observe active galactic nuclei powered by supermassive black holes consuming matter, we're seeing some of the most energetic processes in the universe across distances of billions of light years. These cosmic beacons can outshine entire galaxies, making them visible across vast stretches of space and time. The light we see from the most distant quasars began its journey when the universe was less than 1 billion years old. The cosmic web of dark matter, revealed through gravitational lensing and galaxy surveys, extends across hundreds of millions of light-years. This invisible scaffolding, which makes up roughly 27% of the universe's mass energy, provides the gravitational framework within which galaxies form and evolve. The largest dark matter halos can span millions of light-years, dwarfing individual galaxies. Computer simulations like the Millennium Simulation and the Illustris project model the evolution of cosmic structure across billions of light-years and billions of years of cosmic time. These simulations track the gravitational interactions of billions of dark matter particles, showing how the cosmic web grows from tiny initial fluctuations into the complex structure we observe today. The Vera Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, photographing the entire visible sky every few nights for 10 years. This unprecedented survey will catalogue billions of galaxies across cosmic distances, tracking how the universe changes over time and revealing new insights into dark energy, dark matter, and the evolution of cosmic structure. Neutrinos, nearly massless particles that barely interact with matter, travel across cosmic distances virtually unimpeded. The IceCube Neutrino Observatory at the South Pole has detected neutrinos from sources billions of light-years away, including blazars and other high-energy astrophysical phenomena. These ghostly particles provide a new window into the most energetic processes in the distant universe. The cosmic neutrino background, a relic from the early universe similar to the cosmic microwave background but composed of neutrinos instead of photons, permeates all of space. These primordial neutrinos have been traveling freely since the universe was just 1 second old, carrying information about the cosmos from an even earlier epoch than the cosmic microwave background. Gravitational waves, ripples in space-time itself, travel at the speed of light across cosmic distances. The LIGO and Virgo detectors have observed gravitational waves from black hole and neutron star mergers occurring hundreds of millions of light-years away. These observations provide a completely new way to study the universe, complementing traditional electromagnetic observations with direct detection of space-time distortions. The planned Laser Interferometer Space Antenna, or LISA, will detect gravitational waves from supermassive black hole mergers across billions of light-years. These space-based detectors will be sensitive to much lower frequency gravitational waves than ground-based instruments, opening up new possibilities for studying cosmic evolution and testing Einstein's theory of general relativity on the largest scales. The planned LISA mission will revolutionize our understanding of cosmic distances by detecting gravitational waves that have traveled billions of light-years through space. Unlike electromagnetic radiation, which can be absorbed or scattered by intervening matter, gravitational waves pass through the universe virtually unimpeded, carrying pristine information about the most violent events in cosmic history. When supermassive black holes merge in distant galaxies, the gravitational waves they produce will reach us with their original signatures intact, telling us about events that occurred when the universe was much younger. The concept of cosmic time becomes even more mind-bending when we consider that different regions of the universe are aging at different rates due to gravitational time dilation. Regions with stronger gravitational fields experience time more slowly relative to areas with weaker fields. This means that the universe doesn't have a single, universal now. Time itself flows differently depending on where you are and how fast you're moving through space. The Pioneer and Voyager spacecraft, humanity's most distant ambassadors, are currently traveling through interstellar space at distances measured in light hours and light days from Earth. Voyager 1, launched in 1977, is now over 22 light hours away from us. The radio signals from these spacecraft take nearly a full day to reach Earth, providing a tangible reminder of how even relatively small cosmic distances challenge our ability to communicate across space. The Breakthrough Starshot project proposes sending tiny spacecraft to Proxima Centauri using light sails accelerated by powerful lasers. Even if this ambitious project succeeds in reaching 20% of light speed, the journey would still take over 20 years, and the data transmission back to Earth would take another 4.2 years. This means that any information from our nearest stellar neighbor would represent conditions that existed over 2 decades in the past by the time we receive it. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. One of the key factors in this equation is the vast distances between stars, measured in light years, which make communication and contact between civilizations extremely challenging. Even if advanced civilizations exist around nearby stars, the time delays involved in interstellar communication would make meaningful dialogue nearly impossible. The search for extraterrestrial intelligence, or SETI, faces the fundamental challenge of cosmic distances when listening for signals from other civilizations. Radio waves from a civilization around Alpha Centauri would take over 4 years to reach us, while signals from the center of our galaxy would take 26,000 years. Any conversation with a galactic civilization would span millennia, making it more like leaving messages for future generations than engaging in real-time communication. The Arecibo message, transmitted in 1974 toward the globular cluster M13, will take 25,000 years to reach its destination. If any civilization in that cluster receives our message and responds immediately, their reply won't reach Earth until the year 50,000. This timeline spans longer than the entire history of human civilization, illustrating the profound patience required for interstellar communication. Exoplanet discoveries by the Kepler Space Telescope and the Transiting Exoplanet Survey satellite have revealed thousands of worlds orbiting stars hundreds and thousands of light years away. Each of these planets represents a story that began long before humans existed, and the light we see from these distant worlds carries information about atmospheric conditions, orbital dynamics, and potentially even signs of life from the distant past. The James Webb Space Telescope's observations of exoplanet atmospheres provide snapshots of worlds as they existed years, decades, or centuries ago, depending on their distance from Earth. When JWST analyzes the atmosphere of an exoplanet 50 light-years away, it's studying atmospheric conditions that existed when the first computers were being developed on Earth. Any changes that have occurred on that world since then remain invisible to us until the light carrying that information completes its journey across space. The concept of simultaneity becomes meaningless across cosmic distances. Events that appear simultaneous to us might actually be separated by thousands or millions of years in their local time frames. When we observe a supernova explosion in a distant galaxy, we're seeing an event that occurred millions or billions of years ago, while other events in that same galaxy that appear to happen at the same time might actually be separated by vast periods. The cosmic calendar, popularized by Carl Sagan, compresses the entire history of the universe into a single year to help us understand cosmic timescales. In this calendar, the Big Bang occurs on January 1st, the Milky Way forms in May, our solar system forms in early September, and all of human history occupies just the last few seconds of December 31st. The light-year distances we've been discussing represent the spatial equivalent of these temporal scales. The observable universe has a radius of approximately 46.5 billion light-years, not the 13.8 billion light-years you might expect from the universe's age. This difference arises because space itself has been expanding during the time that light has been traveling toward us. The most distant objects we can see are now much farther away than they were when their light began its journey, carried away by the expansion of space itself. The cosmic event horizon represents the boundary beyond which we can never receive information, no matter how long we wait. Due to the accelerating expansion of the universe driven by dark energy, galaxies beyond a certain distance are receding from us faster than light can travel. Any light emitted by these galaxies today will never reach us, creating a fundamental limit to how much of the universe we can ever observe. This cosmic isolation means that most of the universe will forever remain beyond our reach. The galaxies we can see today represent only a tiny fraction of the total cosmos, and as time passes, even fewer galaxies will remain visible as they cross the cosmic event horizon and disappear from our observable universe. Future astronomers, billions of years from now, will see a much lonelier cosmos than we do today. The multiverse theories proposed by cosmologists suggest that our observable universe might be just one bubble in an infinite collection of universes, each separated by distances that make light years seem infinitesimally small. If these theories are correct, the distances between different universes would be measured in units that dwarf even the largest cosmic structures we can observe. String theory and other approaches to quantum gravity propose that space itself might have additional dimensions beyond the three we experience. These extra dimensions could be compactified at scales much smaller than atoms, or they could extend across distances that make the observable universe seem like a tiny speck. The true nature of space and distance might be far stranger than anything we can currently imagine. The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary, like a hologram storing three-dimensional information on a two-dimensional surface. If this principle applies to the universe as a whole, the vast three-dimensional distances we observe might be projections from information encoded on a distant two-dimensional boundary. Dark energy, which makes up roughly 68% of the universe's energy density, remains one of the greatest mysteries in cosmology. This invisible force is causing the expansion of space to accelerate, stretching the distances between galaxies and eventually carrying them beyond our cosmic horizon. Understanding dark energy is crucial for predicting the ultimate fate of the universe and the future evolution of cosmic distances. The Big Rip scenario, one possible fate for our universe, suggests that dark energy could eventually become so dominant that it tears apart all bound structures, from galaxy clusters down to individual atoms. In this scenario, the fundamental forces that hold matter together would be overwhelmed by the expansion of space, stretching distances until even the smallest particles are isolated from each other across vast cosmic voids. The Big Rip scenario paints a picture of a universe where distances become so stretched that even the electromagnetic forces holding atoms together would be overwhelmed by cosmic expansion. In this far future, roughly 22 billion years from now, space would expand so rapidly that galaxies, solar systems, planets, and eventually atoms themselves would be torn apart. The light-year distances that seem so vast today would become infinitesimal compared to the spaces between individual particles in this ultimate cosmic dispersal. But even without such extreme scenarios, the future evolution of cosmic distances promises to be dramatic. The Milky Way and Andromeda galaxies are currently approaching each other at roughly 110 kilometers per second, and they will collide in approximately 4.5 billion years. This cosmic merger will create a new galaxy, sometimes called Milky, spanning roughly 200,000 light-years and containing over 1 trillion stars. During this galactic collision, individual stars will rarely collide due to the vast distances between them, but the gravitational interactions will fling stars into new orbits spanning hundreds of thousands of light-years. Some stars will be ejected from the merged galaxy entirely, becoming intergalactic wanderers traveling through the cosmic void for billions of years. The night sky, as seen from any surviving planets, will be transformed beyond recognition. The local group, our collection of galaxies spanning roughly 10 million light-years, represents a gravitationally bound island in an expanding universe. While distant galaxy clusters are being carried away by cosmic expansion, the galaxies in our local group will eventually merge into a single, massive galaxy. This process will take tens of billions of years, gradually reducing the number of visible galaxies in our cosmic neighborhood. The concept of cosmic loneliness becomes profound when we consider the far future of the universe. As dark energy continues to drive accelerating expansion, galaxies beyond our local group will disappear beyond the cosmic event horizon one by one. Future civilizations, if they exist, will inherit a universe that appears static and eternal, with no evidence of the Big Bang or cosmic evolution that we can observe today. The cosmic microwave background radiation will also fade and redshift beyond detection as the universe continues to expand and cool. This ancient light, which currently provides our best evidence for the Big Bang and early cosmic evolution, will eventually become so diluted and redshifted that it becomes undetectable. Future astronomers will lose this crucial window into the universe's infancy. Stellar evolution adds another dimension to cosmic distances and timescales. The most massive stars, which can be seen across millions of light-years due to their incredible brightness, live for only a few million years before exploding as supernovae. In contrast, the smallest red dwarf stars will continue shining for trillions of years, long after the universe has grown cold and dark. These stellar lighthouses will be among the last sources of energy in the cosmos. The Gaia space mission has revolutionized our understanding of stellar distances within our own galaxy by measuring the precise positions and motions of over 1 billion stars. This unprecedented survey has revealed that our galaxy is far more dynamic than previously thought, with stellar streams from disrupted satellite galaxies threading through the Milky Way's halo across distances of hundreds of thousands of light-years. Hypervelocity stars ejected from the galactic center by gravitational interactions with our central supermassive black hole travel at speeds exceeding 1,000 kilometers per second. These stellar refugees will eventually escape our galaxy entirely, carrying information about galactic dynamics across intergalactic distances measured in millions of light-years. Some of these stars might even reach other galaxies, becoming the first natural interstellar ambassadors. The study of cosmic rays provides another perspective on vast distances in the universe. The highest energy cosmic rays, particles accelerated to energies exceeding 10 to the 20th electron volts, have traveled across cosmic distances for millions of years before reaching Earth. These particles carry information about the most energetic processes in the universe, from supernova explosions to active galactic nuclei, billions of light-years away. The Pierre-Auger Observatory and other cosmic ray detectors have revealed that the highest energy cosmic rays come from sources within roughly 160 million light-years of Earth. This distance constraint, known as the GZK cutoff, arises because ultra-high energy cosmic rays interact with the cosmic microwave background radiation during their journey, losing energy over cosmic distances. Neutrino astronomy has opened a new window on the universe by detecting these nearly massless particles from sources across cosmic distances. The IceCube Neutrino Observatory has detected neutrinos from blazars over 4 billion light-years away, providing insights into particle acceleration processes in the most extreme environments in the universe. Unlike photons, neutrinos travel through space virtually unimpeded, carrying pristine information across cosmic distances. The upcoming Cherenkov telescope array will detect gamma rays from sources across the observable universe, studying the most energetic processes occurring at distances measured in billions of light-years. These observations will complement neutrino and gravitational wave astronomy, providing a multi-messenger view of cosmic phenomena across the vast scales of space and time. Pulsar timing arrays, networks of precisely monitored neutron stars, are beginning to detect gravitational waves from supermassive black hole mergers throughout the universe. These cosmic lighthouses, spinning with clockwork precision, serve as natural gravitational wave detectors sensitive to ripples in space-time from sources billions of light-years away. The recent detection of the gravitational wave background represents signals from countless black hole mergers across cosmic history. The concept of cosmic archaeology becomes crucial for understanding how structures formed across these vast distances and timescales. By studying galaxies at different distances, astronomers can trace the evolution of cosmic structure from the first galaxies that formed when the universe was just a few 100 million years old to the mature systems we see in our local cosmic neighborhood today. The Hubble Space Telescope's deep-field observations have revealed that galaxy formation was already well underway when the universe was less than 1 billion years old. These ancient galaxies, observed across distances of over 13 billion light-years, appear surprisingly massive and mature for their cosmic youth, challenging our understanding of how quickly large structures could assemble in the early universe. The James Webb Space Telescope has pushed these observations even further, detecting galaxies that formed when the universe was just 300 to 400 million years old. These primordial galaxies, seen across distances approaching the edge of the observable universe, provide crucial insights into the transition from the cosmic dark ages to the first epoch of star formation. The Rayonization of the universe, which occurred roughly 1 billion years after the Big Bang, represents a cosmic phase transition that affected the entire observable universe. During this epoch, the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that filled intergalactic space, creating the transparent universe we observe today across distances of billions of light-years. The 21-centimeter line of neutral hydrogen provides a potential tool for studying the universe before reionization, when space was filled with neutral gas that blocked visible light. Future radio telescopes like the Square Kilometre Array will attempt to detect this faint signal from across cosmic distances, providing a new window into the cosmic dark ages. The formation of the first heavy elements in the universe required multiple generations of stellar evolution across cosmic distances and timescales. The carbon, oxygen, and other elements essential for life were forged in the cores of massive stars and distributed through supernova explosions across thousands of light-years. This cosmic recycling process, operating over billions of years and vast distances, gradually enriched the universe with the ingredients necessary for planets and life. The metallicity gradient in our galaxy, the variation in heavy element abundance with distance from the galactic center, tells the story of chemical evolution across the Milky Way's 100,000 light-year span. Inner regions of the galaxy are more metal-rich due to higher rates of star formation and supernova enrichment, while outer regions retain more of their primordial composition. The metallicity gradient reveals how stellar nucleosynthesis has operated across our galaxy's vast expanse over billions of years. Stars in the galactic center, 26,000 light-years away, show chemical compositions enriched by countless generations of stellar evolution, while stars in the outer halo preserve the chemical signatures of the galaxy's youth. This cosmic archaeology, written in starlight across hundreds of thousands of light-years, tells the story of how our galaxy grew and evolved. The concept of galactic habitable zones extends the idea of planetary habitability to cosmic scales measured in thousands of light-years. Regions too close to the galactic center face intense radiation from the supermassive black hole and frequent supernova explosions, while regions too far from the center lack the heavy elements necessary for rocky planet formation. Our solar system sits in the galactic suburbs, roughly 26,000 light-years from the center, in what appears to be an optimal location for the development of complex life. The Fermi paradox becomes even more puzzling when we consider the vast distances involved in galactic exploration. If intelligent civilizations arise around other stars, the light-year distances between stellar systems would make interstellar travel and communication extraordinarily challenging. Even at significant fractions of light speed, journeys between stars would take decades or centuries, while radio communications would face delays measured in years or decades. The concept of a galactic internet proposed by some CT researchers would require a network of relay stations spanning thousands of light years to enable communication across the galaxy. Such a network would take millions of years to establish and would face the constant challenge of maintaining coherent signals across vast cosmic distances. The engineering challenges would dwarf anything humanity has ever attempted. Breakthrough. Listen, the most comprehensive search for extraterrestrial intelligence ever undertaken monitors millions of stars across thousands of light years for signs of technological activity. The project recognizes that any signals detected would represent communications from civilizations as they existed years, decades, or centuries ago, depending on their distance from Earth. The search requires patience on cosmic timescales. The concept of technological signatures or technosignatures extends beyond radio signals to include megastructures that might be detectable across interstellar distances. Dyson spheres, hypothetical structures built around stars to capture their energy output, could potentially be detected through their infrared signatures across hundreds or thousands of light years. The search for such structures represents a new frontier in SETI research. The WOW signal, detected in 1977, remains one of the most intriguing potential SETI detections. This strong radio signal, which lasted 72 seconds and has never been detected again, appeared to come from the direction of the constellation Sagittarius, roughly 120 light-years away. If it was indeed from an extraterrestrial civilization, we were observing their technology as it existed during the late 1800s on Earth. The concept of panspermia, the idea that life might spread between worlds through natural processes, becomes relevant when considering the vast distances between stellar systems. Meteorite impacts can eject material from planetary surfaces at velocities sufficient to escape gravitational wells, potentially carrying microorganisms across interstellar distances measured in light years. However, the journey times involved would span millions of years, testing the limits of biological survival. The discovery of organic molecules in interstellar space, detected across distances of thousands of light years, suggests that the chemical building blocks of life are widespread throughout the galaxy. Radio telescopes have identified over 200 different molecular species in the interstellar medium, including complex organic compounds that could serve as precursors to biological molecules. The Spitzer Space Telescope and other infrared observatories have detected polycyclic aromatic hydrocarbons, complex carbon-based molecules, in galaxies billions of light-years away. These observations suggest that the chemistry necessary for life might be universal, operating across cosmic distances and timescales that span the observable universe. Astrobiology research increasingly focuses on extremophile organisms that thrive in conditions once thought impossible for life. These discoveries expand the potential habitable zone around stars and suggest that life might exist in environments across vast cosmic distances that were previously considered sterile. From the subsurface oceans of Europa and Enceladus to the upper atmospheres of Venus-like exoplanets, the search for life now encompasses a much broader range of environments. The concept of a cosmic biosphere, life existing throughout the galaxy and potentially the universe, becomes plausible when we consider the vast distances and timescales available for biological evolution and dispersal. If life arose early in cosmic history, it could have had billions of years to spread across thousands of light years through natural or directed panspermia. The anthropic principle takes on new meaning when considered across cosmic distances and timescales. The fine-tuning of physical constants that allows for the existence of stars, planets, and life operates across the entire observable universe, spanning distances of tens of billions of light-years. The cosmic conditions that enable our existence are written into the fabric of space-time itself across these vast scales. The concept of cosmic evolution encompasses not just biological evolution, but the evolution of complexity itself across cosmic distances and timescales. From the formation of the first atoms in the early universe to the emergence of galaxies, stars, planets, and life, the universe has shown a remarkable tendency toward increasing complexity over billions of years and across billions of light-years. The role of supernovae in cosmic evolution becomes apparent when we consider their effects across galactic distances. These stellar explosions, visible across millions of light-years, not only create and distribute heavy elements, but also trigger star formation in nearby molecular clouds through their shock waves. The influence of a single supernova can extend across hundreds of light-years, affecting stellar and planetary formation throughout entire galactic regions. Gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, can be detected across distances of billions of light-years. These cosmic catastrophes, which may result from the collapse of massive stars or the merger of neutron stars, release more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. The afterglows of these explosions can outshine entire galaxies for weeks or months. The concept of cosmic rays as messengers from across the galaxy takes on new significance when we consider the distances these particles travel. High-energy cosmic rays can journey for millions of years across thousands of light-years before reaching Earth, carrying information about the most energetic processes in our galactic neighborhood. These particles serve as natural probes of cosmic phenomena occurring at vast distances. The magnetic field of our galaxy threading through the interstellar medium across the Milky Way's 100,000 light-year span plays a crucial role in cosmic ray propagation and star formation. This galactic magnetic field, though incredibly weak by terrestrial standards, influences the behavior of charged particles across vast cosmic distances and helps shape the structure of the interstellar medium. The concept of galactic ecology emerges when we consider how different components of the galaxy interact across vast distances. Star formation, stellar death, supernova explosions, and black hole activity all influence each other across thousands of light-years, creating a complex ecosystem that operates on cosmic scales. The health and evolution of our galaxy depend on these interactions occurring across its entire 100,000 light-year expanse. The future of human space exploration must grapple with the reality of light-year distances between stellar systems. Even the most optimistic projections for interstellar travel involve journey times measured in decades or centuries to reach the nearest stars. The psychological, social, and technological challenges of such voyages would be unprecedented in human history. Generation ships, hypothetical spacecraft designed to carry human populations across interstellar distances over multiple generations, would need to maintain closed ecological systems for centuries while traveling across light-years of empty space. The engineering challenges would be staggering, requiring life support systems that could operate reliably for longer than human civilization has existed. Generation ships would represent humanity's ultimate commitment to exploring the cosmos, carrying entire civilizations across the light-year gulfs between stars. The passengers who arrive at distant worlds would be the descendants of those who departed Earth, separated by centuries of travel time and countless generations of human experience. These cosmic voyages would need to maintain their cultural identity, scientific knowledge, and technological capabilities across journeys spanning longer than recorded human history. The concept of suspended animation or cryogenic preservation offers another approach to interstellar travel, potentially allowing individual humans to survive journeys across light-year distances. However, the technological challenges of maintaining biological systems in stasis for centuries remain formidable, and the psychological impact of awakening in a completely different era of human civilization would be profound. Robotic precursors to human interstellar missions could pave the way for eventual human exploration, traveling across light years to establish infrastructure and gather information about distant worlds. These artificial ambassadors could operate for centuries or millennia, gradually building the foundation for human settlement while transmitting data back to Earth across the vast distances of interstellar space. The concept of digital consciousness transfer, while highly speculative, offers another potential solution to the challenges of interstellar travel. If human consciousness could somehow be encoded and transmitted as information, it might be possible to send human minds across light-year distances at the speed of light, arriving at distant worlds in years rather than centuries. The philosophical and technical challenges of such an approach remain enormous. The search for potentially habitable exoplanets has revealed thousands of worlds orbiting stars across hundreds and thousands of light years. The TRAPPIST-1 system, 39 light-years away, contains 7 Earth-sized planets, several of which might be capable of supporting liquid water. The Kepler-4 5-2 system, 1400 light-years distant, hosts a planet that might be the most Earth-like world yet discovered. Each of these distant worlds represents a story that began billions of years ago, evolving in isolation across the light-year distances that separate stellar systems. The atmospheric compositions, surface conditions, and potential for life on these planets reflect billions of years of independent evolution, creating a cosmic laboratory for studying planetary science across vast distances. The James Webb Space Telescope's observations of exoplanet atmospheres provide snapshots of worlds as they existed years or decades ago, depending on their distance from Earth. When JWST analyzes the atmosphere of K218b 120 light-years away, it's studying atmospheric conditions that existed when photography was being invented on Earth. Any changes that have occurred on that world since then remain invisible to us until the light carrying that information completes its journey across space. The concept of planetary migration, where planets change their orbits over millions of years, adds another dimension to the challenge of interstellar exploration. A potentially habitable world observed today might have very different characteristics by the time a spacecraft launched from Earth could reach it. The dynamic nature of planetary systems across cosmic timescales complicates long-term planning for interstellar missions. The discovery of rogue planets, worlds ejected from their stellar systems, and wandering through interstellar space reveals another class of objects distributed across the light-year distances between stars. These orphaned worlds, potentially numbering in the billions throughout our galaxy, represent a hidden population of planets that could serve as waypoints for interstellar exploration or even harbor life in subsurface oceans heated by radioactive decay. The concept of stellar engineering, the hypothetical manipulation of stars to extend their lifetimes or modify their properties, becomes relevant when considering the vast timescales involved in cosmic evolution. Advanced civilizations might attempt to manage stellar evolution across their local galactic neighborhoods, spanning hundreds or thousands of light years to ensure long-term energy supplies and habitability. The Kardashev scale, which classifies civilizations by their energy consumption, takes on new meaning when considered across cosmic distances. A Type II civilization, capable of harnessing the energy output of an entire star, would be detectable across thousands of light-years through its infrared signature. A Type III civilization, managing the energy of an entire galaxy, would influence cosmic evolution across hundreds of thousands of light-years. The concept of galactic gardening suggests that sufficiently advanced civilizations might attempt to manage the evolution of life and intelligence across vast cosmic distances. Such efforts would require coordination across thousands of light-years and planning horizons spanning millions of years, representing the ultimate expression of cosmic stewardship. The study of galaxy mergers provides insights into how cosmic distances change over billions of years. When galaxies collide, the light-year distances between their constituent stars are dramatically altered, with some stars being flung into intergalactic space, while others are drawn into the merged galaxy's core. These cosmic collisions reshape the distribution of matter across millions of light-years. The Milky Way's future collision with Andromeda will transform the night sky as seen from Earth, assuming our planet survives the Sun's evolution into a red giant. The merged galaxy will span roughly 200,000 light-years, and the gravitational interactions will scatter stars across vast new orbits. Some stars will be ejected entirely, becoming intergalactic wanderers traveling through the cosmic void. The concept of cosmic heritage sites takes on new meaning when we consider the vast distances and timescales involved in cosmic evolution. The locations where the first stars formed, where the first heavy elements were created, and where the first galaxies assembled represent cosmic landmarks distributed across billions of light-years. These sites preserve the history of cosmic evolution in their stellar populations and chemical compositions. The preservation of information across cosmic distances and timescales becomes a fundamental challenge for any long-lived civilization. How do you maintain knowledge and cultural continuity across journeys spanning light-years and centuries? How do you ensure that important information survives the collapse of stars, the merger of galaxies, and the eventual heat death of the universe? The concept of cosmic archaeology extends beyond studying ancient galaxies to include the search for artifacts left by previous civilizations across galactic distances. Advanced civilizations might leave markers or monuments designed to survive for millions of years, scattered across thousands of light-years as testimony to their existence and achievements. The study of stellar streams, the tidal debris left behind by disrupted star clusters and satellite galaxies, reveals the dynamic history of our galaxy across hundreds of thousands of light-years. These stellar rivers, mapped by the Gaia space mission, preserve information about galactic interactions that occurred billions of years ago when the Milky Way was still assembling from smaller components. The concept of galactic seasons emerges from our solar system's motion through the galaxy's spiral arms over cosmic timescales. As we orbit the galactic center every 225 million years, we pass through different regions with varying stellar densities, radiation levels, and supernova rates. These galactic seasons, spanning tens of millions of years, might influence the evolution of life on Earth across geological timescales. The role of dark matter in shaping cosmic structure becomes apparent when we consider the vast distances over which its gravitational influence operates. Dark matter halos, extending millions of light-years around galaxies, provide the gravitational scaffolding that enables galaxy formation and evolution. Without dark matter, the cosmic web of structure spanning billions of light-years would never have formed. The search for dark matter particles continues in underground laboratories and particle accelerators, but the mystery of this invisible component might only be solved through observations across cosmic distances. The behavior of dark matter on galactic and cosmological scales provides our best clues to its nature, requiring observations spanning millions to billions of light-years. The concept of cosmic inflation, which occurred in the first fraction of a second after the Big Bang, stretched quantum fluctuations across distances that now span the observable universe. The tiny variations in density that would eventually become galaxies and galaxy clusters were amplified from subatomic scales to cosmic scales, spanning billions of light-years in an incredibly brief moment. The cosmic microwave background preserves the imprint of these primordial fluctuations, allowing us to study the seeds of cosmic structure as they existed when the universe was just 380,000 years old. The patterns in this ancient radiation stretched across the entire sky tell us about quantum processes that operated on the smallest scales but influenced the largest structures in the universe. The cosmic microwave background serves as our ultimate baby picture of the universe, capturing the moment when space first became transparent to light across its entire expanse. The tiny temperature fluctuations in this radiation, varying by just millionths of a degree across the sky, represent the quantum seeds that would grow over billions of years into the cosmic web of galaxies spanning billions of light-years that we observe today. The Planck satellite's precise measurements of the cosmic microwave background have revealed that the universe is geometrically flat to within observational error. This flatness extends across the entire observable universe, spanning roughly 93 billion light-years in diameter, suggesting that the actual universe might be infinite in extent. If true, this means that the light-year distances we've been exploring represent just an infinitesimal fraction of total cosmic reality. The concept of cosmic variance becomes important when studying structure across the largest observable scales. Because we can only observe one realization of cosmic evolution, our own universe, there are fundamental limits to how precisely we can measure cosmological parameters. The statistical uncertainties introduced by cosmic variance affect our understanding of structure formation across the largest scales spanning billions of light-years. The baryon acoustic oscillations, regular patterns in the distribution of galaxies across hundreds of millions of light-years, provide a standard ruler for measuring cosmic distances and the expansion history of the universe. These patterns, imprinted when the universe was just 380,000 years old, have been stretched by cosmic expansion but preserve their characteristic scale of roughly 450 million light-years. The Dark Energy Survey and other large-scale structure surveys have mapped the distribution of galaxies across billions of light-years, revealing the cosmic web in unprecedented detail. These observations show that matter is distributed in a complex network of filaments and voids, with galaxy clusters connected by tendrils of dark matter spanning hundreds of millions of light-years. The concept of cosmic walls and supervoids represents structure on the largest observable scales. The Sloan Great Wall, a massive collection of galaxies stretching over 1.3 billion light-years, represents one of the largest known structures in the universe. Conversely, the Bhuta's Void, spanning roughly 330 million light-years, contains almost no galaxies and represents one of the largest empty regions in the observable universe. The study of these largest structures challenges our understanding of cosmic evolution and the role of dark energy in shaping the universe. Structures this large should not have had time to form through gravitational collapse since the Big Bang, suggesting that our models of cosmic evolution might be incomplete or that exotic physics operated in the early universe. The concept of the cosmic web as a living, evolving structure becomes apparent when we consider how galaxies flow along dark matter filaments across hundreds of millions of light-years. Gas streams along these filaments, feeding star formation in galaxies and creating a cosmic ecosystem that operates on the largest scales. The health and evolution of individual galaxies depend on their position within this vast network. The future evolution of cosmic structure will be dominated by dark energy's accelerating expansion. As space expands faster and faster, the cosmic web will be stretched until even the largest structures are torn apart. Galaxy clusters, currently bound by gravity across millions of light-years, will eventually be dispersed as dark energy overcomes gravitational attraction on all scales. The concept of cosmic loneliness takes on profound meaning when we consider the ultimate fate of structure in an accelerating universe. In the far future, perhaps 100 billion years from now, the observable universe will contain only the local group of galaxies merged into a single massive galaxy. All other structures will have been carried beyond the cosmic horizon by the expansion of space. The study of cosmic voids provides insights into the nature of dark energy and the evolution of cosmic structure. These vast, empty regions, spanning hundreds of millions of light-years, are expanding faster than the cosmic average due to their low matter density. Understanding void evolution helps constrain models of dark energy and modified gravity theories. The concept of void galaxies, rare objects that exist within these cosmic deserts, provides natural laboratories for studying galaxy evolution in extreme environments. These isolated galaxies, separated from their neighbors by hundreds of millions of light-years, evolve differently from galaxies in dense environments, offering insights into the role of environment in galactic evolution. The search for cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, involves looking for their signatures across cosmic distances. If they exist, cosmic strings would stretch across billions of light-years and could be detected through their gravitational effects on the cosmic microwave background or through gravitational lensing of distant galaxies. The concept of cosmic topology addresses the question of whether the universe has a finite size despite appearing infinite. If space curves back on itself like the surface of a sphere, light could potentially circumnavigate the universe, creating multiple images of the same distant galaxies. Searches for such cosmic mirages have so far found no evidence suggesting the universe is either infinite or much larger than the observable region. The anthropic principle takes on cosmic significance when we consider that the physical constants allowing for the existence of stars, planets, and life operate uniformly across the observable universe, spanning tens of billions of light-years. The fine-tuning that enables our existence is written into the fabric of space-time itself across these vast scales. The concept of cosmic natural selection, proposed by cosmologist Lee Smolin, suggests that universes with physical constants conducive to black hole formation are more likely to reproduce through quantum processes. If true, this would explain the apparent fine-tuning of physical constants across cosmic distances without requiring intelligent design or infinite multiverses. The study of primordial black holes, hypothetical objects that could have formed in the early universe, involves searching for their effects across cosmic distances. These ancient black holes, if they exist, could make up part of the dark matter and would influence cosmic evolution across billions of light-years. Their evaporation through Hawking radiation could create detectable signatures in the cosmic background radiation. The concept of cosmic phase transitions, sudden changes in the fundamental properties of space and time, could have occurred during the universe's early evolution. These transitions might have left observable signatures in the cosmic microwave background or the large-scale structure of the universe, detectable across the entire observable cosmos spanning tens of billions of light-years. The false vacuum decay scenario represents one of the most dramatic possible cosmic phase transitions. If our current vacuum state is metastable, a quantum fluctuation could trigger a bubble of true vacuum that expands at the speed of light, fundamentally altering the laws of physics. Such a bubble, once formed, would be undetectable until it arrived, potentially ending our universe as we know it. The concept of eternal inflation suggests that our observable universe is just one bubble in an infinite multiverse where new universes are constantly being created. The distances between different bubble universes would be measured in units that make light-years seem infinitesimally small, representing scales beyond any possible observation or exploration. The holographic principle proposes that all the information contained in a volume of space can be encoded on its boundary, suggesting that the three-dimensional distances we observe might be projections from information encoded on a distant two-dimensional surface. If true, the vast light-year distances we've been exploring might be emergent properties of more fundamental information-theoretic processes. The concept of emergent spacetime suggests that space and time themselves might arise from more fundamental quantum information processes. In this view, the light-year distances that seem so fundamental to cosmic structure might be approximate descriptions that break down at the smallest scales or under extreme conditions. The study of quantum gravity attempts to understand how space-time behaves at the Planck scale, where quantum effects become comparable to gravitational effects. At these scales, roughly 10 to the negative 35 meters, the smooth geometry of spacetime might break down into a quantum foam where the usual concepts of distance and time lose their meaning. The implications of quantum gravity for cosmic distances remain largely unknown, but they could be profound. If spacetime has discrete structure at the smallest scales, this might affect the propagation of light and other particles across cosmic distances, potentially creating observable effects in the most precise astronomical measurements. The implications of quantum gravity for our understanding of cosmic distances could revolutionize physics in ways we can barely imagine. If spacetime itself is quantized at the Planck scale, the smooth geometry that allows us to measure light years might be an approximation that breaks down under extreme conditions. This could affect how we understand the propagation of light across cosmic distances, potentially revealing new physics in the most precise measurements of distant objects. The concept of causal sets proposes that spacetime is fundamentally discrete, composed of individual events connected by causal relationships. In this framework, the continuous light-year distances we observe would emerge from the statistical behavior of vast numbers of discrete spacetime events, similar to how the smooth flow of water emerges from the motion of individual molecules. Loop quantum gravity suggests that space itself is woven from quantum loops at the Planck scale, creating a fabric of spacetime with discrete structure. The light-year distances that span our cosmic observations would represent the large-scale behavior of this quantum geometry, much like how the macroscopic properties of materials emerge from their atomic structure. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in multiple dimensions beyond the three spatial dimensions we experience. The extra dimensions predicted by string theory could be compactified at scales much smaller than atoms, or they could extend across distances that make the observable universe seem like a tiny speck in a vast, higher dimensional space. The landscape of string theory contains an estimated 10 to the 500th possible vacuum states, each corresponding to a different configuration of the extra dimensions and different values for the physical constants. If this landscape is real, our universe with its specific light speed limit and cosmic distances would be just one possibility among an unimaginably vast number of alternatives. The concept of brane cosmology suggests that our three-dimensional universe might be a membrane floating in higher dimensional space. Other branes could exist parallel to ours, separated by distances measured in extra dimensions that we cannot directly perceive. Occasionally, these branes might collide, creating new Big Bang events and potentially explaining the origin of our universe. The study of cosmic inflation has revealed that quantum fluctuations can be amplified to cosmic scales, creating the density variations that eventually became galaxies and galaxy clusters. This process connects the smallest quantum scales to the largest cosmic structures, showing how phenomena separated by over 60 orders of magnitude in size are intimately connected. The eternal inflation scenario suggests that inflation never completely ends, but continues in some regions of space while ending in others. This process would create an infinite number of bubble universes, each with potentially different physical laws and cosmic distances. Our observable universe would be just one bubble in this vast multiverse. The concept of the multiverse challenges our understanding of cosmic uniqueness and the significance of the distances we observe. If infinite universes exist with every possible combination of physical laws, then the specific light-year distances that characterize our cosmos might be just one realization among infinite possibilities. The anthropic principle attempts to explain why we observe the physical constants we do by noting that we can only exist in universes where the constants allow for the formation of stars, planets, and life. The cosmic distances that enable stellar evolution and planetary formation across billions of light years might be necessary conditions for the existence of observers like ourselves. The fine-tuning of physical constants becomes even more remarkable when considered across cosmic scales. The strength of gravity, the mass of the electron, and dozens of other parameters seem precisely calibrated to allow the formation of cosmic structures spanning light years to billions of light years. Even tiny changes in these constants would prevent the formation of stars, galaxies, or the complex chemistry necessary for life. The concept of cosmic natural selection proposes that universes with physical constants conducive to complexity and structure formation are more likely to reproduce through quantum processes. This could explain the apparent fine-tuning without requiring intelligent design or infinite multiverses, suggesting that the cosmic distances we observe are the result of a kind of evolutionary process operating on the largest scales. The study of dark energy and dark matter reveals that the universe is dominated by components we don't understand, operating across the largest cosmic scales. Dark energy, which makes up roughly 68% of the universe's energy density, is causing the expansion of space to accelerate, stretching the distances between galaxies and eventually carrying them beyond our cosmic horizon. Dark matter, comprising about 27% of the universe's mass energy, provides the gravitational scaffolding for all cosmic structure. Without dark matter, the cosmic web spanning billions of light years would never have formed, and galaxies as we know them could not exist. The nature of dark matter remains one of the greatest mysteries in physics. The concept of modified gravity theories attempts to explain cosmic acceleration and galactic rotation curves without invoking dark energy and dark matter. These theories propose that Einstein's general relativity breaks down on cosmic scales, requiring modifications that could affect our understanding of distances and cosmic evolution across billions of light years. The Vera Rubin Observatory, currently under construction, will survey billions of galaxies across cosmic distances, creating the most comprehensive map of cosmic structure ever assembled. This survey will help resolve questions about dark energy, dark matter, and the evolution of cosmic structure across the largest observable scales. The concept of cosmic archaeology extends beyond studying ancient galaxies to understanding how information is preserved across cosmic distances and timescales. The light we observe from distant objects carries information about conditions that existed billions of years ago, creating a fossil record of cosmic evolution spanning the entire observable universe. The preservation of information across cosmic scales faces fundamental challenges from quantum mechanics and thermodynamics. The second law of thermodynamics suggests that information tends to become scrambled over time, while quantum mechanics imposes limits on how precisely information can be stored and transmitted. Understanding these limits is crucial for interpreting observations across cosmic distances. The concept of cosmic censorship, proposed by Roger Penrose, suggests that the universe has built-in mechanisms to prevent the formation of naked singularities that would violate the predictability of physics. This principle might extend to other aspects of cosmic evolution, ensuring that the universe remains comprehensible across all scales from quantum to cosmic. The black hole information paradox raises fundamental questions about the nature of information and its preservation across cosmic scales. If information falling into black holes is truly lost, this would violate quantum mechanics and challenge our understanding of how information propagates across the universe. Recent developments suggest that information might be preserved through subtle quantum correlations, but the resolution remains controversial. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, implying that the three-dimensional cosmic distances we observe might be projections from information encoded on a distant two-dimensional surface. This radical idea could revolutionize our understanding of space, time, and cosmic structure. The concept of emergent space-time proposes that space and time arise from more fundamental information-theoretic processes. In this view, the light-year distances that seem so fundamental to cosmic structure might be approximate descriptions that emerge from quantum information processing at the most basic level of reality. The study of quantum error correction in space-time suggests that the universe might have built-in mechanisms to protect information from corruption across cosmic distances and timescales. These mechanisms could explain why the laws of physics remain consistent across the observable universe, and why information can be reliably transmitted across billions of light-years. The concept of cosmic computation proposes that the universe itself might be performing vast calculations as it evolves, processing information across cosmic scales. In this view, the evolution of cosmic structure across billions of light-years might represent the universe computing its own future, with galaxies, stars, and planets serving as components in a cosmic computer. The search for signatures of quantum gravity in astronomical observations represents one of the most ambitious goals in modern physics. Effects that are negligible at everyday scales might accumulate over cosmic distances, potentially creating observable signatures in the most precise measurements of distant objects. The study of gravitational waves has opened a new window on the universe, allowing us to observe space-time distortions from sources across cosmic distances. Future gravitational wave observatories will be sensitive to ripples from the early universe, potentially revealing information about cosmic inflation, phase transitions, and other exotic phenomena operating across the largest scales. If you made this far, make sure to subscribe to the channel and give this video a like. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. The harsh reality of why we can't travel at light speed. In this video, we reveal the tough reality behind the universe's ultimate speed limit and why the speed of light is an unbreakable barrier woven into the fabric of space-time. See you there.